All right. Well, good Wednesday morning. Welcome back to another fun-filled day of calculus. Our plan today is to carry on with our discussion last time. You may remember that I showed you Rolle's theorem, right? And Rolle's theorem seemed kind of like a silly little theorem, basically saying that if you've got a function who's continuous and differentiable in an interval, and the endpoints of the interval have the same y, then somewhere in between, there's a point that has a derivative of 0. So, yay. So what? Well, we're going to see that we're going to use Rolle's theorem to prove what's called the mean value theorem, or sorry, the mean value theorem, not to be confused with the extreme value theorem. But we're going to prove the mean value theorem, and it's that theorem that's actually important. And we'll see what that tells us. And basically, we're going to start investigating what the derivative, the second derivative, what that kind of stuff tells us about functions. So that's our plan. Before we do that, though, any questions on any of the homeworks or anything else that we've been talking about the last couple of days? All right, well, hearing and seeing none, then I guess we'll go ahead and switch over to the whiteboard. So I will be right back. All right, so last time we proved Rolle's theorem. Let me just remind you what Rolle's theorem says, and then we'll see why we actually care about that one. So Rolle's theorem looked a little bit like this. It says that if we have a function that is continuous on a closed interval, so an interval that includes the endpoints, and differentiable on the open interval. So it doesn't actually have to be differentiable at the outsides, okay? It just has to be differentiable in the middle of it. So think about how that could play out. We could have something that has like a vertical tangent line, a kink, or whatever. As long as those are happening at the endpoints of the interval, we're still okay. It just has to be continuous throughout and differentiable in the open, right? But then, and we had to have one more thing, which was that f of a equals f of b. So we get the same function value on two sides. Then, let me change color here for the then part. So then, there exists a c that's in the interval AB. Now, I'm going to show you another symbol that I've not shown you before. It's mathematical shorthand. I've been wanting to use it a whole lot, but I didn't want to use it without introducing it to you. But this little guy looks like a little E, kind of like a little curvy capital E, or a C with a line in it. This literally means contained in. So this is just a math way of saying there's a C that's in this interval. It's just a lot faster. So when I do theorems, I'm going to want to use this a bit. So just so you know, and this isn't a Bruce-ism. This is a technical math symbol. You look at any kind of math paper, scholarly work, you'll see that. Okay, so then there exists a C that's in this interval AB such that, and believe it or not, there's also a symbol for such that. There's also a symbol for there exists. Mathematicians are awesome. And in fact, I'll show you how we write that in math in just a second. But there exists a C in AB such that f prime of C equals 0. All right, so we saw this last time. You don't necessarily need to, rewrite it. But basically what this said is that if we've got a function where the two endpoints have the same y value, so say here and here, right? So there's A and there's B, then somewhere between A and B, because it's continuous and differentiable, there's a place such that the derivative is equal to 0. So just to kind of remind you, we had to do that in 3 cases. The first case was if it's constant throughout. Well, okay, that was our third case, I think, but that's the first one I'll talk about. So that one, if it's constant everywhere, then clearly the derivative equals 0 because the derivative of constants is 0. The second case was there's some point that's above, and if there's a point that's above, the reason that we knew that there was going to be a place where the derivative is 0 is from the extreme value theorem, right? The extreme value theorem says that on a closed interval, if you've got a continuous function, you're guaranteed an absolute max and an absolute min. Well, the absolute max is going to have to be somewhere above A and B then. And we saw that the only time we could have extrema is at a critical point. Critical points where the derivative was 0 or undefined. But since it's differentiable everywhere, that forces the derivative equals 0. Third case, same story, just there's some point that's below AB. Well, now there's a minimum somewhere. Same argument. There has to be a place where the derivative equals 0. Okay, so that was Rolle's theorem. And like I told you, on its own, it doesn't really do anything for us. But what we're going to do is use this to prove this next theorem, which definitely matters. So this one's called the mean value theorem. And as always, I'm going to abbreviate it as the MVT, not MVP, right? Not the best player, but it's the best theorem, right? So it's been voted MVT for hundreds of years. Oh, sorry. All right, so mean value theorem. I'm a little punchy, again, after a super long day yesterday. All right, so mean value theorem. How this plays out. All right, so here's the deal for the mean value theorem. We're going to go with actually the same beginning as Rolle's theorem, that we've got a function that's continuous and differentiable. All right, so this starts with if f of x is continuous on the closed interval AB and differentiable on the open interval AB. Okay, so it's starting exactly the same. But the thing that's a little bit different now is we're not forcing f of A to equal f of B. Not saying that these 2 points have to be equal in terms of their y. They can be, one can be higher than the other. All right, so this is it in terms of the ifs. But then here's the then. So then, okay, there exists, and here you go. I'm going to show you the map notation. So then, there exists a C contained in AB such that f prime of C equals f of B minus f of A over B minus A. So real quick aside, you can, I don't know if you can tell, I've got kind of a little shit-eating grin on my face because I just threw the math notation into, I just want to show you this real quick. So you see this right here? Check out how many words are in there. Two words, then and A, but everything else tells, so then there exists a C contained in AB such that, man, mathematicians are great. We also got another one, this one, upside down A, for every. So that means for every. Okay. So in actual English language, so then there exists a C contained in interval AB, and this vertical line is such that. Anyway, just a glimpse into the absolute laziness of mathematicians. We invent symbols for words and phrases. Anyway, so don't worry about that. Let's think about what this theorem is saying. So we've got a continuous function, right? No holes, no jumps, nothing like that. It's differentiable. So no kinks, no vertical tangent lines, right? Okay, so that's all you got to have is a continuous differentiable function. If you have that, then what the mean value theorem says is that somewhere in the interval, there's a place where the derivative, prime of C, is equal to this quotient right here, f of b minus f of a over b minus a. Anybody recognize that? Anybody recognize that fraction?
Is it slope?
It
Or like
is,
distance between 2 points?
it's totally slope, right? It's the change in the y divided by the change in the x, right? You also saw it in the difference quotient, right? And I see Ollie just put in the chat. It was the delta y over delta x, right? We saw this when we built the derivative. Remember the limit definition of the derivative? It was the limit as x approaches c of f of x minus f of c over x minus c. That's exactly this, just with different letters. Okay, so here's what this is saying. The bit that's on the right, the f of b minus f of a over b minus a, this is the slope of the secant line. And I'm going to put here that connects the endpoints. Because A and B, those are the ends of the interval. Okay, so we're just looking at those two, find those 2 points on the graph, connect them. The slope of that line is this guy right here. Well, what's f prime of c? Well, this is also a slope, right? But what kind of line? I know it's early. There you go. Thanks, Bailey. Tangent line, right? So this guy's the slope of the tangent line. All right, so basically what this theorem is saying is that somewhere in the interval, as long as it's continuous and differentiable function, somewhere in that interval, you're going to find a point where the slope of the tangent line is equal to the slope of the secant line over the interval. Okay, so that's what this is saying. Let me draw a picture so you can see what's going on. But we'll make some generic function here. Let me make it so that the endpoints are definitely not even close to being equal. So here's some sort of a function. Say that this is A and this is B. So we've got our 2 points that are the endpoints of our interval. You connect them, right? There's our secant line. So this red line is a secant line. And what the mean value theorem tells us is that there's going to be somewhere in this interval where we're going to find a tangent line that has the same slope. Okay, so let me show you where one would be. If I kind of come up to like right about there, I've got a point such that its tangent line is parallel to the red one. I know they're not exactly parallel, but just imagine. This would be a C that makes that happen, right? So here is a point that's somewhere in the interval AB where we get a tangent line that has the same slope as the secant line. Okay, so hopefully you can see that. This is also a good example because there's another one. Do you see another place where we actually have a tangent line that's parallel to the secant line?
The trough.
Yeah, down here in the trough somewhere, right? Like, I don't know, right about there. Let's just go with it. Right, so that's another parallel line. So somewhere down in this trough, there's another one. So first notice that this theorem doesn't say there's only one C where this happens. It just says that there is a C where this happens. So you might have more than one. I mean, you could have 38 of them, depending upon what your function looks like and how big the interval is. But what this theorem tells us is that we're guaranteed to find one. Okay. In this case, there are two. So before we prove it, let me just tell you why it's called the mean value theorem. And let's think about this from like a velocity standpoint, because that's kind of how we started with derivatives, right? We kind of argued finding derivatives looking at velocities. So think about this. The slope of this red line, if this is position, and this guy, the slope would be the average rate of change. Right, so it'd be the average velocity. It would be the, okay, we've got this pen flying through the air, hit my stopwatch, let it go for a little bit, hit it again. I look at how far it traveled over that amount of time. Boom, there's my average velocity, my average rate of change. But then we saw that derivatives gave us instantaneous, right? So if we take like this green line, its slope, this is the instantaneous rate of change. So what the mean value theorem is doing is saying is that somewhere in this interval, you are going to get an instantaneous rate of change that's equal to the average rate of change over the entire interval. And that's why it's called the mean value theorem, because think about what mean means in math. It means average. So this is a theorem about the average value. It's the average rate of change. That's what our value is. So that's why we call it the mean value theorem. All right, so we cool with what it's saying? How we feel about that? Thumbs up if you're okay with it. Okay, cool. Seeing lots of thumbs up. That's what I like to see. All right, so it's not that big of a deal in terms of what it's saying. It's once you kind of read through it, you see what it means. So let's prove it. Let's actually see why this must be, and then we'll talk about what it's good for, because it's good for a lot of things. All right, but here comes our proof. Now, to prove this, here's what we're going to do. I'm going to make a new function. Okay, I'm going to make a new function, and what it's going to be is actually made up of two different functions. The two different functions that we're going to look at are the function that we're given. So I'm just erasing these tangent lines because they're just going to get in the way. But we're going to look at this function, the blue function, and we're going to look at the function that we create with this with these two dots. So we're going to look at that secant line. Okay, so let's first start with the secant line. And let's get its equation. So what we need, of course, for a secant line is a slope and a point, right? For any line, you need to know a slope and a point. Now, the slope we know, right? Its slope is going to be f of b minus f of a divided by b minus a. Right? Calculated slope. We also need a point on it. And we have a couple of choices. We can use either one of the ones on the outside here. So I'm going to go ahead and just use f of b, if you guys don't mind. So we're going to have a point that's b, f of b. So if you know the function and you're told a and b, this is what you would do to calculate a slope and a point. Right? You just plug b into the function, boom, there's that point, and then b and a into the function, find the slope, we're good to go. So that means that its equation is actually y equals f of b minus f of a over b minus a times x minus b plus f of b. And I'm going to preemptively answer the question that just popped up in somebody's head. Where'd you get that? I know some of you are thinking that. Where'd I get that? I just used the point slope form. I don't know if you remember that, the y minus y1 equals m times x minus x1. Okay, so I just use that. This is what happens when you plug in all the different things. Okay, so just smile and nod, if you would. All right, so there's the equation of that secant line. All right, well, now that I've got that, I'm going to make a new function. And we're going to look at g of x and what g of x is going to be is f of x minus this line. Now, it's at this point you're probably going, why? Who cares about this thing? This is sort of the miracle step in showing this proof, is just to create this thing. It's the difference between our function and the secant line. Okay, so what it's going to look like then, g of x is going to be f of x minus the thing that I just wrote up here. So then minus f of b minus f of a over b minus a times x minus b plus f of b. Okay, so for some reason, we're looking at this weird ass function, which is the difference between the function and the line. Okay, so I know at this point you're still probably like, whatever. Well, now I want you to look at g of x, specifically at the endpoints at a and b. What do we get? Remember what this is the difference between our function and the line. What's the difference between the function and the line when we're out here at a? What's the difference in those y values?
It's a smaller one.
Yeah, it's pretty small.
And it's increasing.
What specific value is the difference between these?
Oh, b minus a.
Not b minus a. Think about at this one point right here. Remember this is the gap between the red and the blue, right? That's what this is saying. What's the difference between the red and the blue? What's the difference between the red and the blue when we're out here at A? All right, thanks. Ollie just put in there 0. There is no difference. They're the same point. What about out here at B? What's the difference between those two, the red line and the blue graph? This is when Ollie just hits enter again, right? So 0, also 0. Both of these things have exactly the same value at those ends. So check out what we know about g of x. G of x is such that g of a equals 0 and g of b equals 0. Okay, so now let me remind you about Rolle's theorem. So Rolle's theorem said if we have a continuous differentiable function whose endpoints have the same value, then there's somewhere in the middle where the derivative has to equal 0. Okay, well, with g, we've got our endpoints being the same, but let's just talk about real quick, is it continuous and is it differentiable? Well, it is the difference of f of x and y. F of x is continuous because we were told we needed that. Is y continuous? What's y again? Y was that line. So are lines continuous? This is when everybody gives me the thumbs up, the head bobs, the absolutely, right? Lines are continuous. So if I have two continuous functions that I subtract, it's still continuous. So g of x is definitely continuous. Is it differentiable? Well, f of x is differentiable because we're told that it is. Is the line differentiable? Again, this should be when there's the resounding absolutely, right? Does this have a derivative? Yeah, it's the slope of the line. So the difference of differentiable functions is also differentiable. So this thing that we just created, g of x, it is such that it's continuous and differentiable. The endpoints are both equal to the same value. So we can apply Rolle's theorem. All right, so here's where we're going to actually use Rolle's theorem. So by Rolle's theorem, we know that there is a place where the derivative of this equals 0. Right? So we know that there's going to be some place where g prime of c equals 0 somewhere. Okay, so let's find that. So let's take the derivative of g. So g prime, it's going to equal f prime minus y prime. Right? When you've got two functions being subtracted, we saw that rule a long time ago, that you can differentiate each one separately and subtract. All right, so there is going to be some place where this equals 0. And that's going to be when we plug in c. So we're going to get f prime of c and then y prime. So if I just manipulate this equation, I get f prime of c is equal to y prime. Well, y prime, since y is a line, y prime is its slope. Okay, well, its slope, as we saw up here, is f of b minus f of a over b minus a. And that right there, I don't know if you guys were all paying attention, but that was the result of the mean value theorem. The slope of the tangent line somewhere is equal to the slope of the secant line. All right, so there's your proof of the mean value theorem. It absolutely has to be true. It has to be true because of how derivatives work. Okay, so there you go. Let me show you an example. Let's actually take a function. Let's apply the mean value theorem to it. to show you how this plays out, and then we'll talk about what it's good for. But before I show you an example, any questions on the proof? Or are you even to a point where you can visualize a question here? And I'm less concerned that you know the proof or can replicate the proof. I'm less concerned about that than knowing what the function says. And it seemed like you guys were pretty good with that. I was getting a lot of thumbs up. Then this happened. So if you're confused, just back up to that time, that happy time, like 5 minutes ago when you were all giving me thumbs up. Just remember that, right? All rainbows and unicorns. All right, so let me show you an example. So super easy function. Let's just go with, say, f of x equals x cubed. And let's look on the interval 1 to 3. So first, consider the conditions necessary for the mean value theorem. Is this function x cubed continuous on that entire interval and differentiable with the possible exception of the endpoints?
Yes.
And yeah, we're good. It's a polynomial. We know polynomials are always continuous and differentiable. All right, cool. So we know that we can actually apply the mean value theorem. So let's start by finding what that average value is, what that mean value is. Let's find the slope of the secant line. So I'm going to look at f of b minus f of a over b minus a. All right, so this is going to be 3 cubed minus 1 cubed over 3 minus 1, which is 26 over 2, or 13. Okay, so that's the slope of the secant line between 1 and 3. It's the average rate of change on this function from 1 to 3. All right, so that's, now what the mean value theorem says is that there is some place then where f prime of c equals 13. So let's find it. So let's look at the derivative. The derivative is 3x squared. So if I plug in c, it's going to be 3c squared. So c squared is 13/3, or c is equal to plus or minus the square root of 13 over 3. All right, so I know you don't like that number, the square root of 13/3, but it's a number that's just slightly bigger than 2. Right? 12/3 is 4, square root of 4 is 2. So 13/3, since it's a little bit bigger, its square root's going to be a little bit bigger than 2, but it's definitely less than 3. So it's 2 point something. So we have two possibilities: something that's slightly bigger than 2, or something that's really close to negative slightly bigger than 2. Well, if you look at this positive one, the square root of 13/3, this guy is between 3 and 1. And remember, we were told that there's gonna be a point somewhere in this interval where the derivative equals this average value. And there it is. We just found it. All right, so it just guarantees this point. Now, this is a place at this step, or at this point in time, you might just go, all right, this is just more, yay, we know that a point exists, big